This is the C1 January 2012 paper. I'm just going to go through questions 8 and 10. First of all, question 8, a bit of differentiation. So let's go through this bit by bit. To differentiate this, the first thing to do is to multiply out the brackets. So when we do that, we've got our expression, our equation in index form, and then we can just differentiate them term by term. So the first term will differentiate, so we're looking at dy by dx. First term multiplied by 3 times x, and then reduce the power by 1. And the second one we multiply by the power, so that's 2 lots of 2x and reduce the power by 1. And then we can just simplify that. So there we have it. The dy by dx is 3x squared plus 4x. So y is a cubic, which means it's going to have 2 turning points, and it'll either start low and end up big, or it'll start big and end up low. Well, when x is large and positive, this x cubed expression here, term here, will become very, very large. It will become larger than the x squared term. So when x is very large and positive, in other words, we're moving along the x-axis here, the y-coordinate is going to get much bigger. So it looks like we're going to be in this scenario here. When x is very large and negative, we're going to have negative times negative times negative, so it's going to be a negative number. So as we move towards the x value in this direction, the y-coordinate is going to get lower and lower and lower, so we're going to be in this scenario. So this is the situation. We're looking at a curve that's going up, down, and then up. So let's just have a quick look at our gradient, and the gradient expression here, 3x squared plus 4x, that's a quadratic, so that will be equal to 0 in at most 2 situations. In fact, if we put that equal to 0 and we factorise in this way, we can see that when x is equal to 0, the whole expression will be equal to 0, or when x is equal to minus 4 over 3, the whole expression will also be equal to 0. In other words, we've got 2 turning points at those x coordinates. And just looking back at our little sketch above, that's when x is 0, that'll be this point here, this turning point here, and when x is minus 4/3, that'll be this turning point here. So the last thing we need to be able to do our sketch is just to work out where is it going to cut the x and y axes. We've already established that when x is equal to 0, the y-coordinate will be equal to 0, so we know where it cuts the y-axis, and just by factorising back to our original form of the equation, we can work out when the y-coordinate is going to be equal to 0, in other words, when will it cut the x-axis. Well, clearly that will be when x is equal to 0, or when x is equal to minus 2. So let's put that all together then on our sketch. We know that it will cut the x-axis at 0 and minus 2. It cuts the y-axis at 0, and we know that it's this general kind of shape that we had up here. So what we've got is a curve that goes up, comes down, and then goes back up again, like that. For part C of the question, we're asked to find the gradient of the curve at each point where it meets the x-axis. We've already established that it meets the x-axis here and here, so we just need to substitute those values for x into the differential equation to find out what the gradient will be at each of those points. So we're looking at 3 times 0 squared plus 4 times 0, which is equal to 0, and we're looking at 3 times minus 2 squared plus 4 times minus 2, which is equal to 12 minus 8, which is equal to 4. So the answer to this one is 0 and 4. And for part D of this question, we started off with our first curve, C1, of y equals x squared lots of x plus 2, and we're given now a new curve, C2, x minus k all squared, lots of x minus k plus 2. Well, if our original curve was, let's call it f of x, x squared lots of x plus 2, what we've now got for the second curve here is a transformation of that original curve. So that is going to become f of x minus k. Wherever we see x in our original equation, we're replacing it with x minus k in the new equation here. So that is, it's a transformation of the original curve. As we know, when we transform a curve in this kind of way, what it's effectively doing is moving the curve 2 places to the right, or no, sorry, k places to the right in this case. We're told that k is greater than 2, so that's going to give us a bit of a clue about how far it's going to move to the right, but essentially what we've got to do for this question is just move the whole of our original sketch to the right by more than 2. So if we move this curve by more than 2, this point here is going to move to the right of the y-axis, and this point here is going to move over here. So we're going to have k, this point, the 0 moves from 0 up to k, we're adding k to it, and then this is going to be just to the right of the axis here, so this point is going to move over to here. So when we sketch that in, it's going to look something like this, there, and all we've got to do is just work out the coordinates of this point here where it cuts the y-axis, the x-axis, and this point here where it cuts the y-axis. Well, this point here is easy because it's just simply minus 2 plus k, minus 2 plus k. And for this point here, where does it cut the y-axis? Well, simply it's got an x coordinate of 0, so we have to plug x equals 0 back into our original equation, and then just simply multiply that out. So just simply plugging in x equals 0, we're going to end up with a value for y of minus k cubed plus 2k squared. So that's what this one's going to be, minus k cubed plus 2k squared. In question 10, we're given a curve C with this equation here, and we've got to find out the coordinates of point A for the first part of the question. Well, at point A, we've got to find out the x-coordinate. Clearly the y-coordinate is equal to 0, so we've simply got to rewrite our equation as y equals to 0, so 0 is equal to 2 minus 1 over x. In other words, 1 over x is equal to 2, or x is equal to a half. So the first part of that question is pretty straightforward. For the second part of the question, we've got to work out the equation of the normal to see at point A. So first of all, we've got to find out what the gradient A would be. We've then got to find out what the gradient of the normal would be, in other words 90 degrees to that, and we've got to put that information together with the fact that we know the coordinates of A to work out the equation of this line, which is the normal here. And then finally we've got to rearrange that to get this format that we're given in the question. So we'll start a new page for that one. So first of all, the coordinates of A were a half, 0, and now we've just got to work out the differential equation for y. So we're looking for dy by dx. Well, before I work out dy by dx, I'm just going to rearrange the original equation in index form. So that 1 over x becomes x to the minus 1. And now we can differentiate that term by term. The 2 is going to disappear, and we're looking at minus 1, the power, times negative x, and then we decrease the power by 1, as we can see there, and just rearrange that. So dy by dx is just simply equal to 1 over x squared, or just x to the minus 2. These minus signs cancel out here. So the first part of this there, or the next part of this, is when x is equal to a half, what would that gradient have been? Well, the gradient would be equal to, so at x equals a half, dy by dx is equal to 1 over a half squared, which is equal to 4. So the gradient of the normal here is simply minus 1 over that, is equal to minus 1/4. So we now know the gradient of the normal that we're trying to work out. So we've got the gradient of the normal, we've got the x-coordinate of the normal, and we've got the y-coordinate of a point on the normal, so we can just use our simple equation. Y minus a particular y point over x minus a particular x point is equal to the gradient of a line, and just substitute in the values we know. So y minus 0, that's the y-coordinate, over x minus a half, which was the x-coordinate, is equal to minus 1/4, that was the gradient of our normal. If I now multiply both sides of my equation by x minus a half, I can start to untangle this and try to get it to look like we want it to from the question. Multiply out the brackets, and then multiply through by 8. Then add 2x to both sides and subtract 1, and we've got normal in the format that they wanted in the question. So now we have to move on to part C. So in part C we've got to try and find the coordinates of point B up here. So we know that the equation of the normal is 2x plus 8y minus 1 is equal to 0, and we know that the equation of the curve is y is equal to 2 minus 1 over x, and we know that coordinate A is a half 0. So we know when we basically got to put together these equations and solve them simultaneously, one of the solutions is going to come out that x is equal to a half. So we already know the y coordinate that corresponds to that. So it's the other point that we're interested in, where those two, where that line and that curve crosses over. So let's write them out as simultaneous equations, and then we'll just simply substitute y is equal to 2 minus 1 over x into our first equation. And then if we just tidy that up a little bit by multiplying out the brackets, then gather like terms and multiply through by x, we've got ourselves a quadratic equation to solve for x. So you could do that by completing the square or using the quadratic formula or by factorising, but what you'll find is that there are two solutions to that. X is a half, which is the one that we've already seen earlier in the question, or x is equal to minus 8. So x equals minus 8 is going to be the x coordinate for B, and now we've just got to substitute that into either one of these two equations to find out what the y coordinate is going to be. And I've done this into the curve, so that we see that the y coordinate is 2 and 1/8. That means that the x coordinate was minus 8, the y coordinate was 2 and 1/8, and that is our answer.